Thank you guys for having me. Very happy to be here and share some really cool content with you guys. So where we left, where Doug left us off last week, was in really breaking down how we do science. And so we started with establishing what is this shared reality, establishing really an object to study, something that we can agree on, establish some kind of notion of objectivity to. And we accomplished this through modeling. And so I wasn't here, so I don't know exactly what was talked about, but I trust that Doug taught you guys about the differences between modeling and theory, how models are integral for connecting theory to reality, and how theory is necessary for helping us make sense of models and for building some kind of cumulative knowledge. And after that, he took us kind of on this side detour into thinking about what is the scale dependence of this reality that we're measuring, the models that we're using, the theory that we're probing. And this is kind of the central concept of what I'm going to be talking today. What is the scale that we are asking these questions at? When we're talking about social systems, that could be on the scale of the individual, of the neighborhood, of the city. In the physical context, it could be on the scale of the atom, or of the gases of a room, or a nebula. And of course, we would want some kind of connectivity between these scales. And that's what a lot of emergent phenomena is really about. But the example that he gave last week was of Conway's Game of Life, where we got to see, so from some really basic rules, we had some relatively arbitrary shapes that could move. Those shapes could move or stay stationary, could interact with each other. They could form really complex objects that, when you zoom out, look like pixels again. And then we kind of took you on this circular path of emergence. Well, there was a couple of issues with that demonstration, not Doug's fault, but some issues that we're going to resolve today during class. The first, of course, is the circularity. In reality, we don't know for certain. If you zoom out on the universe enough, do you get just an atom again? It could be, we don't know yet. But we'll take that to be not true. Of course, we kind of glossed over the fact that you could zoom out, and that you could go from image 1 to image 2 to image 3. Of course, there is some kind of process by which you can drop all of the mechanisms that were at that small scale. And we call this coarse graining, we call this averaging, different people call it different things. There's a whole field of physics dedicated to just this process of rescaling a system called renormalization. But how does all that even work? And in what cases can we actually, so to say, renormalize? We're not going to talk about that today. That's a whole other discussion. But then, the last and really important thing is that this Conway's Game of Life was really just a model. There's no real theory behind how these ought to behave, how they do behave, what they represent in life, other than just kind of some kind of reproducing quantity. And so when you approach that as a scientist and you ask, well, what can I learn about this system? Well, in reality, when people are trying to probe Conway's Game of Life and ask what's next, it's all guesswork. There's no really guiding principle for finding new starships or swimmers or whatever they call them. And so to illustrate the kind of problem this creates scientifically for exploring Conway's Game of Life, if we just ask what information can you enclose in this little box here, we have a 1,000 by 1,000 roughly. I just kind of eyeballed that. That means you have this many options of pixels. That's an unfathomably large number. For reference, there are that many atoms in the universe. So we have a couple of thousands of millions of orders of magnitude difference. So if we ask, what does science do in this context when we have a really large space of possibilities, theory and science helps us narrow that down. And to illustrate this with a more intuitive example, if I'm a doctor and I'm treating a patient, my treatment is not going to involve shooting them into the sun. And that sounds obvious, of course, because we have all these theories about how suns work, what bodies need, how those two things are incompatible for treatment. So hopefully this helps with some motivation for where does emergence come from, and how do we need to think about it as a scientific problem. So we're going to be talking about emergent phenomena today, and I'm going to lead off this discussion with another example, and then walk you through how some of these mechanisms work. And so we're going to use a case of driving. Hopefully it's something that we can all kind of relate to as we, maneuver around the world in our lives. And so we're going to start with, as we did in the case of Conway's Game of Life, with just establishing the rules. So what are the rules of driving? How do you drive? Can anybody tell me? Yep. Stay inside the lines. We have some boundaries. We have a fixed track that you need to figure out how to navigate. What else? What can you do, or what ought you do? Yeah.
I'm saying that the goal is not to crash.
The goal is not to crash. Let's focus on what we should do first.
Okay.
And then, yeah. Like, how do you operate a car?
Oh, just steer left and right.
So you have steering, right? Okay.
Stay on the right side of the road.
You have an orientation on the road. Yeah.
The right pedal's fast. And the
Exactly.
left is
So we have to
slow.
move. We have to move. We have to steer. We have to follow some laws. Right. Exactly. So we can list these rules, these basic functions, going forward and backing, shifting gears, steering, braking. I didn't give you guys a chance to say this, but you also need to signal to there's some kind of interaction with other drivers. Okay, so now what can't you do in a car? Yeah. Okay, so I haven't thought of that, but yeah, okay, yep. You cannot fly, so you're stuck to the ground. Exactly. There's a really big one that we should definitely establish before we get behind the wheel. Anybody? Don't crash the car. Okay. So we have these rules that go along with our functionality. So, and we've talked about a lot of these already. Okay. Don't hit each other. That's really big. And so driving, when you put it this way, driving is really simple, right? You can go from having never touched a steering wheel to legally being able to operate a vehicle in any state in this big country we live in, or most of us live in, within 6 months, and then apply for an international license and so on. So does this mean necessarily that driving and that traffic is simple? Anybody? No, it's not. And to illustrate some of the emergent complexity that we get from just these basic rules, here's like a minimal illustration of how traffic works. What do you guys see here? Yep.
Reaction times takes one driver a little bit of a second to match the speed or stopping of the driver in front of them.
Right, so we're starting to see, maybe we could have put in a basic function here, a reaction time, but we see now these reaction times couple with each other, and that causes some funky behavior. Anybody else? Okay, so the one thing I really want to highlight is that you can if you squint a bit, you can kind of make out objects forming here. In science, we would call these objects, but they're really more of like, what's the word, like an apparition maybe. It looks like there is sort of, some kind of thing propagating here, right? Like a wave of some sort. And this is a bit of a hint of how we study these things. But this emergent phenomena that we are observing generally is traffic. And so this is a subject of intense study by traffic engineers, by traffic scientists, and so on. And we can demonstrate what this looks like, what we saw in the last frame, really simply here, where say we have some kind of obstruction that's removed. That obstruction causes an accumulation of cars. As we pointed out, those cars have some reaction time that's going to dictate how quickly they start moving again. But what we see as a stopped object here is moving backwards, right? So now we have something that's moving in a direction that nothing else is moving in. So what? Right? So traffic jams propagate in the opposite direction of car flow. And this is a really basic case that we can hopefully relate to of emergence. And the thing I want to highlight in this case is that this emergence came from like really simple rules. We didn't even really describe how these cars are interacting. And even more importantly, we had no way of predicting that these wave fronts would have occurred. All we had was just these basic rules. I mentioned nothing about wave mechanics, and suddenly we're seeing something that looks like it could follow the same math as like a sound wave or a light wave. And so we can see this emergent phenomena that connects already to a bunch of other theory that we already have, even though the basic underlying components were completely unrelated. And the really important thing that we've uncovered here by going from the scale of the driver to the scale of traffic is we kind of erase some of the agency that the individual drivers have. Because say one driver is like a Formula One driver, he's, has impeccable reaction time, et cetera. He's not going to do anything to help this, even if he's in the middle of it. And so this is all to say that, better drivers might not necessarily solve traffic. We are really we're pushing up against what, this idea of individual agency. And so, like I said before, this emergent phenomena is the subject of intense study. And so there are theories of traffic congestion where we have fancy things called phase transitions. And so just to give you an illustration of what's happening in this plot, imagine we have these two quantities that we can measure about this population, the vehicle density, so the number of cars per unit area, and the vehicle velocity, which is like on average how fast cars are going. And we can ask for a population of cars for some traffic jam. We can ask like, where does this instance of traffic fall? And we see when we make this plot that there are two regimes of traffic. One is what we call free or synchronized flow, where essentially everybody's moving at a speed of their choice. These interactions aren't, weighing down the flow of traffic by too much. And as long as for a density, you have some velocity that's sufficiently high enough, you can stay within this free flowing regime. But as soon as you slow down too much, or as soon as you get too dense, you're suddenly in this traffic or in this congestion zone, where you're kind of at the mercy of these emergent effects that individuals can't really affect. And so when we study emergent phenomena, there's a lot of discussion of these phase transitions. How do we characterize them? Where they come from? How avoidable are they if you're really into analyzing policy? And what really delineates a phase transition from other types of phenomena is that it's where small changes in the behavior or in the characteristics of your system causes a massive change in the observables. All we've done to go from this side of the line to this side of the line is we've added maybe 5 more cars, right? Which isn't that much, or maybe 5 cars per unit area. So in some cases, these phase transitions can be really delicate. And so just to give you, now that we understand kind of what's going on, we can examine this across scales. Well, if we ask the individual scale that we talked about here just now, it's the car. And then that car can be put on a road, and now we have this phenomena that is the road. But we can take a step back even further and ask, well, how does this affect the transportation network of a whole city or a metropolitan area? And we can start to ask, here's a map of Los Angeles. Anybody here who's grown up in Los Angeles knows how frustrating this image and relatable this image is. What this says is, if you want to go what could be a 5-minute drive, it's not going to be an hour. So what is this now? How do we study this? And so when you want to study a phenomena across different scales, you also need to recognize that because there's different phenomena at different scales, you study them in entirely different ways. So when we study the individual in the case of traffic, we're studying gas usage. We're interested in the safety of the driver. How do we keep this driver on the road? Whereas if you're a traffic engineer, and actually before I get there, so these would be questions for like an engineer, like a safety engineer, for an environmental engineer who's trying to make gas more fuel efficient. If you're studying traffic on a road, you're interested in flow rate, density, local pollution. Whereas if you're studying an entire transportation network, well, now we're thinking about gross emissions. We're thinking about these large population level measurements. You're thinking about land usage. Is a big topic these days is whether this approach to moving people around is actually does it make sense? Should we be using trains? Should we be using bikes instead? So you can start to really ask new questions, the more emergent phenomena that you reveal in your system. And so you can imagine, back in the day, 100 years ago, when we were really, as a society, moving too slowly to worry about high-speed traffic or to worry about flow across an entire metro area. The big questions were in how do we move? How do we build a car? How do we build faster wagons? But now that that transportation as a field has gotten so big, we're really thinking on the level of states, cities, countries, etc. But just because we can think about that big scale and those big scale questions, these smaller scale questions still matter a lot. Okay. And so just to recap, you know, every scale matters, every scale is really important, even if these large scales do reduce and are composed of these smaller scales. And again, you know, we've shown you cases where, you know, these relatively simple rules aggregate to give us this interesting phenomena, but this doesn't necessarily have to be true. I could have given you something like, you know, quantum mechanics, which is a pretty complicated micro theory that gives us equally complicated macro theory, which eventually gives us life, right? So these emergent cases can be really complex all the way through. But what we do see commonly, and this is what allows us to do all the interesting science, is that once we do that renormalization step, once we average to the larger population, you know, some of the individual features matter a little bit less. And so we can study these levels independently of one. Are there any questions so far? Yeah.
Just want to also, you talk about how you, when you look further out and you look more broadly, that the individual matters less.
Yeah.
I was kind of thinking about when you have marching, when you have these platoons, and it's because the individual decides at the second to walk forward, that it then kind of comes as a group, rather than it being like the road traffic thing.
Yeah.
How do you square those kind of two things?
No, that's a really, really cool question I've never thought about. And I think we got to ask what's the goal of the march. And the goal of the march is to make the entire army look like one person. Right. So you're asking for this really precise corner case of a crowd where individuals aren't distinguishable. And so for that, you have really delicate conditions. And equally, sometimes when you look at phase transition diagrams for certain phenomena, you get like really, and this is common in like the quantum engineering world, you have really delicate, really useful phases that are really hard to get to. And it's why why the city of Chicago is investing billions of dollars in a facility on the south side. It's so that we can, you know, figure out how to achieve the march, right, so to say. So it's a matter of like what space in that phase diagram are you trying to operate in or trying to achieve? Any other questions? Okay. And so before we continue, just want to talk about these definitions. The first being this concept of scale. And I hopefully we can kind of intuit this by now. You know, there is a notion of, you know, what scale are you measuring this at? That scale is defined relative to other things. So you usually have to establish like, you know, what's composing this phenomena that we're studying at this scale. And then just this concept of emergence that that we can study this scaled out phenomena independently of its underlying components. So does anybody have any questions about this before we move on? Great. Okay. And the last thing is, you know, I've kind of gone back and forth about, you know, how important is the smaller scale. Is it some cases it is, some cases it's not. The important thing is that you just can't, or this notion of scientific reductionism is thrown out the window for complex systems. Because it's, I mean, you could technically like aggregate from the level of the car to the level of the road network. It would just be incredibly computationally expensive to the point of being like totally infeasible. You could derive Newton's laws from like quantum mechanics, and people have done that to show that, you know, this emergence works. But for the sake of, you know, playing football, you're not thinking about like quantum entanglement, right? You're just throwing a ball and expecting gravity to do its job. So at some level, you know, we don't want to reduce to fundamental components, but we want to keep in mind that, you know, we can often rescale over these sometimes simple, sometimes complex. Okay, so I've introduced complexity through this relatively relatable phenomena of traffic. Now we can talk about like a pretty compelling scientific example, and that's segregation. And so, of course, let's motivate this, why study segregation? What do we expect to learn by treating segregation as this emergent phenomenon? Well, it's really just to understand like why, how, like where does this come from? Is this something that policy could solve simply? Is this something that teaching people to be more tolerant could solve quickly? You have all of these kind of nebulous questions about how you address a problem, but to actually answer them, we should probably figure out how it works first. And so, to motivate this model, I'm going to show you guys. Like, let's just imagine we had a bunch of people on a grid, and I think actually scan this while I'm talking, and then I'll keep talking. So there's a QR code on the board for anybody. People in the back, there's a QR code. Everybody got it? Okay. So, yeah, so we're going to make an assumption that segregation could emerge from people having this kind of preference for living with people who may look like them, may not look like them. We would call this some kind of predisposition for homophily or heterophily. And so then we have to actually model this. We have to ask, well, how similar are you to your neighbor? How do you identify some in-group versus some out-group? How many of your neighbors are around you, for example? And then how many empty houses are there around you? So you guys, so now that we have some ideas of what might go into the simulation or what might go into this problem, in order to simulate this and to study it in this really controlled environment, we would have to kind of operationalize these questions or these assumptions. And so to operationalize this, well, you have to make some definitions. You have to narrow down, and this is really like a guide to how do you model anything. What system are you actually going to study if you're studying segregation? What are the objects? Are we studying like infrastructure? Are we studying people? What are we allowing those people to do, et cetera? What are the rules? How do they move? Can they move? When do they move? How often? Things like that. And then the question would be, what phenomena do we observe? Hopefully, and I think what Schelling did is show that we can, from answering these questions, we can come up with something that that illustrates segregation. Okay. So now that you guys have that the app pulled up. So what I want you guys to do is set the parameters of that model to these values, and then click run and see what happens. Yeah.
You go back to that.
Yeah. Okay, so what are we seeing, guys?
So massive dividing when you get one island of red.
Okay.
Pretty even red and blue, and then one island of red in the blue.
Okay. Is everybody seeing something similar? Anybody seeing anything different? What shape is the island you're seeing?
So like, it looks a bit like Australia.
Okay.
No,
Yeah. So is everybody seeing Australia, or is everybody seeing something different? So there's a cool observation there that with these similar rules, we're getting I'm guessing everybody's getting different things. So you can see with just these simple ingredients plus some randomness, you get pretty diverse set of outcomes. Anybody else? Okay, so now change similarity to 76% and see what happens. Somebody different, tell me what's happening. Somebody who hasn't spoken yet.
I don't think much happened, but maybe like the empty houses, there was a few more in between the red and blue. Let's see. Didn't change much.
Is that true for everybody else?
We mentioned reset and then run or?
Oh, yeah,
Oh, okay.
reset, yeah, try that.
We don't see it forming a similar cluster
Yeah.
as before.
Yeah. Is anybody seeing clusters form? So, I was talking about something, some kind of transition earlier. Does anybody remember what that's called? Phase transition. Do we think this could be one of them? By changing this parameter by 1%, we've gone from total order, we've gone from Australia and whatever other continents you guys were seeing to just like static, right? Can anybody maybe come up with the reason why?
Well, in this case, the satisfaction is low, and so people, like everyone, is moving all the time.
Mhm.
But then since the similarity threshold is that little bit higher, they're not able to find any places where they're consistently happy. So it's just constantly moving.
So that's almost there. So we know why increasing similarity might cause this phase transition, but why specifically 75 to 76? I'll wait for somebody else. Yeah.
Sure how the algorithm does it, but it's possible that it considers like all of the tiles adjacent to itself, in which case it's like a multiple of 4.
Yep.
Number of tiles that are adjacent to it.
Yep.
At which point, like 76% means you need all 4 to be the same.
Exactly. So what's happening here is everybody's looking for the case where all of their neighbors look exactly like them. And unless you are like, if you're on the boundary, that's never possible because there's always going to be somebody different. So you're going to want to move. If you're on the inside, you're cool. But as soon as the guy next to you moves, you're going to want to move next. So you enter this regime, and I kind of skipped over what the rules of how does the simulation actually work, but we've kind of uncovered it here, where every time step, every round of the simulation, everybody's basically asking themselves, like, am I happy with these neighbors? And if they're not happy, there's some chance of them moving. If they are happy, they'll stay put. And then I believe they're moving to a random place on the map. I'm not too sure about that detail, but it's exactly this geometric argument that if you're on the boundary, you'll never be happy, you'll move, the boundary moves, and then we're back to where we started. And so that's exactly a phase transition. And, you know, for the scientific merit of this model, you know, obviously there's never this realistic case where I want 76% in my square neighborhood. That's impossible, so I'm going to move. That doesn't happen in reality. But we do see that when you have some kind of threshold for preference for your neighbors, you're going to stay put, or you're going to seek some place that satisfies that. So we've kind of identified some kind of behavior in people that might result in segregation completely independent of some policy environment that they live in. Did I just give away the next slide? Maybe. But you know, this is the full explanation of what's happening. You know, we reached a steady state earlier. We've disrupted that steady state by changing this parameter, and now we're seeing just total disorder in our model. And so now you guys can just play around with it. Turn the knobs, the dials, see what you see. Play around for a few minutes. And then if along the way you have questions about what some number might do, we can, you know, raise your hand. In your view, what might be the most important parameters? Is it that neighborhood or that neighbor preference? Do you see any other cases where this order or disorder vanishes? Any fun observations so far? Yep.
Like lower the similarity to a certain point, smaller clusters get.
Okay, so we see this relationship between cluster size and preference for similarity. Yep.
Like a significant number or like majority of either red and blue, it still has like the same phenomenon where it basically just keeps going for currently like an indefinite number of rounds. I don't know what round it will stop, but it seems
Yeah.
like even though most of the red clusters, if I set like it to be a red majority, they kind of stop moving, but then the blue, the remaining blue dots, they continue to just shift around because they're not satisfied. There aren't
Yeah.
enough blue dots for them to.
That's a great point. So earlier we saw a case where there's total freezing of our neighborhood. So there's other cases where segregation could persist but be highly dynamic. So there's a third phase maybe of the simulation. Anything else before we move on? Yep.
Saying, like, segregation, that there is a portion of the map that stays like consistently red. So in a way, like the blue has been cordoned off, it's just that the blue is moving around within that area.
Okay, yeah. So we see some kind of boundaries for forming some, yeah, that's really cool. So you can see the richness of this simulation with just a few really simple assumptions. But the main thing, hopefully we've gathered from this is that these phase transitions are pretty strong. To go from that totally locked up case that we started with to the noisy case we had to essentially reset. I'm sure you could have changed some other parameters that we didn't touch to get you out of there, but in general, these phases are robust. So next question, what are we missing from this model? Would you say this is a good model for housing and for neighborhood choice? Do you think this should be used for policy making? What do you guys think of this model? Yeah.
Seems to imply that all parties have the freedom to move and equal opportunity to move.
Right.
Now,
Right.
something I've ever seen happen.
Yeah. So we're in a bit of a fantasy world here. Yeah.
It also has that segregation is the only like factor that people consider when choosing.
Exactly. Like we have, there's no costs, there's no physical boundaries. Yeah. I mean, our identities red and blue, like are we that binary? Sorry?
Sorry, that was what I was gonna.
Oh, sorry.
No, that's okay.
Yeah. Yeah.
Basically just like there's very few ways in which we have any kind of like homogeneous in only two ways.
Mhm.
I think that we can use to model it.
Yeah. No, and this is a really important point because so just to take a step back and actually let's look at this. Well, actually, before we look at that, so this model that you see here basically kicked off like an entire field that now has conferences every year with thousands of people attending regularly, and it's the computational social science. This showed that we can probe social phenomena with like basic rules and a computer and simple computational resources, and we can learn a lot. We can explore all these different phases. We can play with identities, et cetera, et cetera. But at the end of the day, these are really simple abstractions. We've made people red or blue. We've said there's no cost moving, right? But we've still gathered some, what I'll talk about later, as stylized facts about reality. So to that end, there's a lot of missing features. And here's a list of some of them. There's no geography, there's no necessity, there's no points of interest, there's no utilities, there's nothing really that makes this in any sense real. All we have are just identities and spaces for those identities to fill. But we still can learn something kind of interesting. Any questions on this before we move on? Okay. And so lastly, I think, how well do you think the agents in the simulation model real people picking their neighborhoods, knowing that we've kind of skipped over a lot of what we important features? And then by extension, what can we actually learn from people specifically? Let's start with like a simple yes or no. Raise your hand if this models people well. Raise your hand if you think it doesn't. Okay, I saw no yeses, which is like the right answer. The right answer is no, right? So then why is this useful if this isn't even, these aren't real people? Anybody? Yeah.
It shows us something about how what impact small minute decisions can have. On
Yeah.
It's kind of like this emergent.
Yeah. Did you have something back there? Sorry.
Yeah, I was gonna say like, now that you're starting to model things, like you can simulate it, and so you don't have to rely on like real life scenarios. So yeah, you can develop it more and make it more accurate.
Yeah. So we have a starting point. Exactly. So what we're kind of implying here is going to be a topic of discussion in a couple of weeks. What we as scientists call orders of understanding. Another way to look at this is that, we're just asking what's one of the features, what's one of the inputs that could affect segregation. To address that first point, well, you could hypothesize that maybe it's preferences and identities that is the driving factor behind segregation. And then you can start by building having preference dynamics on a really simple grid. We introduce more features to this grid eventually. What we should expect as scientists is that what we observe in these really simple general cases should hold later on as we add more features. And if those, if for some reason when we add roads, we don't see segregation anymore, well, that means roads are doing something wildly phenomenal that transcends human choice, right? So by establishing that choice here is what matters. So we can start to build this puzzle and like lay this roadmap of what might be the components of segregation here. And so to this orders of understanding, this is kind of implying that choice is the first order, but we could have also done any other modeling choices that could prioritize other things. Yeah. Oh yeah. Yeah.
It's like phase transitions for these tipping points require like consistent behavior that like have patterns emerge as a result.
Yeah.
And it just really feels like in real life this like never happens because like in order to have that consistency you need people to behave in like exactly the same way across different individuals. So like do we ever actually see these sorts of phase transitions in the social sciences? Is it like worth like chasing after them?
Yeah.
Or like as like a tipping point for analyses?
Yeah. Well, before I answer that directly, I'll just bring up the case of physics because that's where we get this language from. So I think the first model that showed phase transitions was the Ising model, which is where the Ising model essentially is a Schelling model, but we replace people with colors to essentially like a magnet where you're either north facing or south facing. And this idea is that this array of magnets, depending on how they're oriented and depending on how they flip, can be used to study how actual magnets work. Where if you have everything is blue, then you have one kind of magnet. If everything's red, you have a different kind of magnet. And if everything's kind of flip-floppy, you have no magnet. And so you could ask, well, how well does the Ising model like approximate reality? And very luckily it does, but it wasn't guaranteed to. So, and there's been other cases of really helpful, clean models in physics that don't have a realistic analog, but we still study them in order to learn about how certain kinds of phenomena interact. So then if we take that intuition into the social sciences realm, well, unfortunately, we don't, to my knowledge, have like the data, the time, the legal infrastructure to ask these questions, the ethics, if we threw everybody into like a model city and, played this forward. So yeah, you're right that there's limits to how well we can like test the Schelling model or something similar in a real case. But what we can ask from this is, can we at least produce segregation from some notion of preference? And assigning some kind of observable, like segregation to some kind of characteristic of somebody like a preference now gives you at least some motivation to ask some more specific, verifiable scientific questions, right? So something like this is, and if you guys know more, please interrupt me. But the goal of a really abstracted model like this is to just inspire more questions. Now, when you have more data, yeah, what's up?
Hop in a little bit. Remember, we discussed models as a way to explore and narrow our questions, right? Right. I said that the zooming out gets really complex, and so I was going to leave it to our complexity scientists. Part of what we're looking at here is a lot of big decisions, for example, in policy. When you zoom out, you don't know what's going to happen, but you can use these to get first principles that guide what occurs, whether or not you agree with the model that underlies it. There's been a ton of decisions made about the economy, about crime, about policing, about the environment, etc., that all are based on some underlying model, and then what people believe will abstract out of it. And so there's sort of two arguments. One is any successes there, or some successes show that finding these first principle or second principle or first order and second order causes gives us tools to investigate, narrows our questions, allows us to find useful things. And if you're a cynic and you believe that all of it is worthless, which you're allowed to believe that if you want, at the very least, all these discussions are happening in this language. And so even if you don't believe any of it is useful, you have to know how to engage in that language to argue against a model that you might disagree with.
Yeah, and to go off of that, like I talk to people all the time who like think what I do, I don't do this, but they think what I do is like total nonsense. Like what can data really tell us about people? And so, as Doug says, just having the language to have that discussion, and to also have the, if you're interested in this type of work, to have the humility to, really say like, okay, we're making a lot of assumptions here. The predictive power is pretty limited, right? So engaging with this type of work can be, it can be kind of delicate. Okay, so I want to move on unless there's another like pressing question. Okay. Okay. So just to recap, what we saw here is how these individual choices of individual cells can result in some kind of emergent phenomena. And, just removing one cell or changing the preferences of one cell wasn't really going to change that. This is really what we call population effects. And so this is a case, moving into the upshot, this is a case of what we call agent-based models. And this is, in the last 10 years, this field has really taken off. When you go to like computational social science conferences, everybody's talking about this. And so it's a really big thing. And, we're to answer or to address some of these questions, the calibration techniques for really fitting this to data, having enough characteristics to fit the data is pretty limited. And so historically, this has been used to establish what we call stylized facts. For example, that segregation could emerge from some kind of preferences among people. But like the case that we saw before, this was an emergent phenomena. This resulted from some kind of simple decision. And we can, the whole frontier lies in adding heterogeneity to these decisions, adding, more features to the model, et cetera. So if you're interested in reading about this is kind of related to the work I do. There's a book, Making Sense of Chaos, where they talk about how agent-based models are being used right now to develop new models of the economy. And that kind of, essentially all the things that standard macro econ does, and also what they avoid in trying to develop their models, ABMs are trying to attack head on, and kind of, stir some controversy. So if you're interested in reading more about how ABMs are used and potentially could be used, check out this book. And, of course, there's an entire field dedicated to like this type of research called complex systems. So I encourage you guys to look into it. Okay, so that concludes the first part of the lecture. And I think we're probably going to end a little bit early today, which is okay.
Can I ask a
Yeah,
question?
yeah.
Connect to the DAGs that Doug was talking about. How would you reflect that in, in these kind of causal diagrams?
Yeah. Were you going to say something?
You can take turns on this.
Oh, yeah. So, yeah, I kind of totally avoided this. emergent phenomena kind of don't deal with causality. Because we can identify mechanisms that could influence, what. Okay, there's a bit of a difference in what like physicists consider. When physicists says X causes Y, they don't mean it in like the causal sense of like the arrow pointing in a direction. They mean that these two phenomena are related. And that's to describe one you have to, or one can't be described without the other. So in that sense, like individuals don't cause traffic. Traffic is just another way of looking at individuals moving around. Does that make sense? So to bring this back to the question of causality, they're often not interested in studying causality. They're really interested in establishing like what is the phenomena that we're seeing, what contributes to that phenomenon. And then causality comes in trying to study like what are some interventions that we can make. So if say I have that Schelling model from some, say we had Australia and I wanted to add New Zealand next to it, a policy question could be like, well, how do I seed, New Zealand? Like, what do I need to, can I just like add 3 people there and then that'll kind of, turn into a thing. So in that sense, causality is a way to probe how do we interact with this system and how do we change this system. But in terms of how we describe it as an emergent phenomenon, we're not interested in causality necessarily.
I think I already sort of covered a little bit on this idea of zooming out versus zooming in with our models. And emergent phenomena, the reason I didn't talk about zooming out is because when we zoom in, we can construct something. We can look at the object. We're often observing the smaller object. And we can then construct and observe what a model of their behavior is. But for zooming out, that isn't in our immediate field of view. And so suddenly it's a whole other consideration, equally important. Someone asked about implications, for example. How do we think about the implications of something? Part of the reason that implications are complicated is because it requires modeling beyond the initial system, because we have this propagation of effects, right? If I punch a wall here, someone's going to run outside, they're going to talk to the security guard guard's going to go over there, you're going to go talk to your friends. All of a sudden we have all these other objects, and as time goes on, this effect propagates through space and time and other objects quite dramatically. And so thinking about this zoom out or emergent phenomena is important but difficult, but a sort of necessary step to reason about what are implications we couldn't have thought of. How can we model our current system to find implications we hadn't thought of that we should think about in order to make an informed choice about our options?
Yeah. And so there's a question that comes from this, which is why is emergent phenomena only happening now? Why didn't you guys learn about this growing up? Like why when you took your intro psych class or intro social class, like why are these taught as like separate fields that might not connect? And that's because, like Doug has implied, the only reason why we can like really look at these phenomena across scale is because we have data and because we have the computational tools to probe the relationships between data at different scales. So the goal of people like who wrote that book I showed you, the goal of these, maybe you've heard of like Mansueto, like these highly interdisciplinary research centers, they're really like probing this frontier of what data can teach us about connecting things across scale. So this is kind of like a hot topic and like new kind of way to look at social systems in this like really integrated, scale dependent way.
But if you want to design interventions, but the connection between causality and emergence isn't quite clear, where do you anchor the intervention, right? So for instance, let me give you an example. There was a recent op-ed in the New York Times by Jennifer Walker, who was making a point that, some of the problems we have with bureaucracy in the US and globally are emergent in the sense that there is no one person or group of people who said, we want to create a sucky system, but there's some problems that emerge by a lot of individuals following some rules that individually made sense, but in the aggregate didn't make sense, right? And so then how do you intervene, in a system like that when the causality isn't quite clear?
Yeah, I mean, this is a really like deep question, and it's kind of some would say this is why like revolutions happen in some cases where, you know, society becomes educated enough to realize that the way something was working doesn't work, and then it blows up. But the way to think about it in terms of what I taught you guys today is, you know, you get into some phase of operation of your system, and it really takes somebody who has that language of like complexity to attribute that to being to something that you can turn the knob on. It takes a different kind of thinking is really what I'm trying to say. And so that would be on the diagnosis side. And then on the actual application side, it takes communicating that, convincing people that, you know, we can study government as, you know, an emergent system that has, you know, and I'm sure you guys have seen like those political compass memes, right? Where it's like, are you authoritarian or liberal or left or right or whatever? Right, like that's, you know, they put that as kind of a joke, but it's telling us something that there's a set of choices of policy and cultural choices that lands us in the aggregate at some part of that quadrant. And so the scientific question could then be like, what are the knobs that, you know, move us around that political spectrum? And it's you know, it's absolutely an oversimplification, you know. That's kind of the renormalization is by definition kind of a simplification. So the question then is like, well, what's the right kind of simplification? Can you make it? You can't always make it. So to answer that question, it really turns into this multifaceted problem of scientific diagnosis, of communication, and then of actual problem solving, which is, if anybody's telling you the field is remotely close to that, they're lying. It's not, it's like not nearly there. Yeah. Okay. Moving on, ready to move on? Any other questions? Okay. All right. So now between, you know, we've been talking to you guys about these last few weeks, we've really set up this problem of theories and models and reality. And we've been telling you how important it is to be able to interact with reality, but we haven't told you how to do that yet. And that interaction can happen through sensing, through measurement. And so the next part of this lecture and what we're going to talk about tomorrow, next Thursday, is how we accomplish that through using the use of instruments. And so before we get into that discussion, I'm going to ask you guys a question. We're doing this question?
I
Okay.
think you already answered that question maybe 2 weeks ago. Remember?
Yeah, so we don't need to.
Okay.
But remember
Okay.
the answer was pretty optimistic.
Yes. It was like 2 was the mode.
Four.
I mean 4. Thank you. Yes, 4 was the mode.
Nice. That's a very optimistic place to be. Okay. Good. The important thing to know is that there is no agreement on what the answer to this question is. Definitely across fields, even within scientific disciplines. And we can always ask, of course, why does this matter? Well, this matters, like I said, depending on what you do for your profession and what ways you're trying to contribute to science. So if we think about biologists, for example, most of what we know about biology has been through like direct observation through a microscope, through electronic microscopes. We can see these cell pathways, these signaling pathways, etc. We can establish a pretty like real, literal model of how people work. Whereas economists, you know, because they study a much less tangible emergent system, you know, they have to rely more on kind of, I don't want to say guesswork, but a lot of I don't know what word can I use? Theorizing, assumptions. You know, to make economics work, you have to, you don't have the luxury that biologists have. And so economists are usually empiricists, and there's usually a lot of disagreement on what's the best model for projecting, you know, the green energy transition and so on. So we would consider economists usually the empiricists. And then we have fields like physics, where it really depends on what type of physics you're doing. So if you are a, let's see, if you're a particle physicist, actually, no, let's not use that. If you are, so there used to be a field called kinematics. It's mostly figured out. It's the field of the study of how things like move through the air, how gravitational bodies interact. It's what you studied like in your intro high school physics class. That's a pretty realist field, right? Like we can drop the ball, we can throw the ball, we see what happens. Versus if you are a quantum mechanic, quantum theorist or a quantum experimentalist, you're really relying, you're playing with Schrodinger's cat all day, more or less. That's a pretty like not tangible, difficult to probe system. So this is all to say that depending on what type of physics you study, you could rely on just empirics, or you could rely on a pretty real interpretation of reality. And every century or so, all of physics is turned on its head, and what we thought was true isn't true anymore. But getting back to this point of what does it mean? Well, what does this mean for the universe, right? If something so fundamental like how a particle might behave is really subject to whatever scientists are feeling that century, what does that mean for like how we do science? Or at least, in the context of this lecture, how we measure, how we observe. So we can just think about that and move on. So for now, let's put our realist hat on, and we can ask this question of measurement, establishing a scientific fact of this room. How many people are here? Let's just say it's 20. Similarly, are there people in this room? Yes, right? So, I mean, this is kind of a review on facts and values. Any guess on which is which? Yeah.
One's values, second is fact.
Yep, exactly. So the way that I ask these questions, one, we can make that distinction, but I could have asked this in a different way that made them both fact-based. If I had said, are there a lot of people in this room? I could have said, are there more or less than 10? And Eamon talked about this distinction in the first lecture, so we don't need to spend that much more time on it. But the point of this is that, as we figure out how to reframe these questions in like a fact-based way, we can gain information to that answer through some kind of direct observation. We've been answering these questions using our eyes, and then hearing each other, and then getting that answer from each other. But I could have asked you like a much more difficult question, like what's the average height of the room? And then you might need a tool or something a bit more, something beyond just your eyes to answer the question. But at the very least, these eyes are telling us something real about our room. And, something that's really rich about just observing with your eyes is that they tell you something a bit more. They leave open questions for what you can probe further with, for example, the use of tools. And that's something like a history of a person, right? So like, I know there's people in this room now, but where did they come from? Why are they here? Where are they going to be here in an hour? Hopefully not, if they have, other obligations throughout the day. So these, how we observe the world could lead to questions of, what might we want to ask next, and so on. So, like I said, these are all facts that we can establish directly, but how can we establish these indirect questions of, for example, where will you guys be in an hour? How could I measure that? Yeah.
Survey us.
Okay. So I would employ a tool called a survey, and that could introduce you guys could answer it faithfully or not, could introduce some bias. Yeah. I could use a tracking device, exactly. So I would have you guys sign permission slips, and then I'd hand you a tracker, and then I would take some data. Once you get into measuring people, there's a lot of legal regulations you need to follow. But there's a way, there's a method. But there's, you know, the beauty of these two answers you guys gave us is that they have very wildly different, people could disagree wildly on how reliable they are. You know, if you had somebody who didn't believe in GPS, who thought the world was flat, they might say this, you know, the data that you collect from this GPS is nonsense, right? Similarly, somebody could say the survey, well, you know, I lied, I'm guessing everybody else lied. How can you believe it? Right? So there's usually not a gold standard. I've given you cases where, you know, that flat earth example, we can prove scientifically that it works, so that's not as big of a problem. But the main point is that the way that you measure something indirectly, or at least through some tool, could introduce a lot of uncertainty from how that tool works. And we've seen this, and this deficiency is what has inspired technological innovation throughout the years. You know, if we take, for example, clocks, that was initially some, you know, crude, you know, measurement of angles of the sun with the earth through sundials. And now, you know, fast forward 2,000 years later, we can measure the decay time of an electron in an atom deep beneath the earth, et cetera, et cetera, et cetera, with like infinite, you know, crazy precision. So in those 2,000 years, we innovated a lot, we refined a lot, and we now, you know, we have much more precise measurements. The same thing can be said for temperature and for many other things. Now, there's sort of a burden of proof here when you want to, for example, make not just an innovation, but when you want to establish two different tools for measuring the same thing. And that is this concept of agreement. So, for example, if I really believe these GPS results, I could ask whether that agrees with some kind of direct observation. If I hire people to stand at every corner, right? If I wanted to believe, and then I can establish that the GPS works, then I can validate that with the survey. And this is to say that, you know, if we were to introduce new tools, we need some way of, you know, asking whether this works or not. And, you know, I started with this example of people's eyes, but we encounter this all the time where people's eyes aren't even all that reliable. People's memories are fallible. So we sometimes find ourselves in these weird cases where what we are calibrating our new tool to might not even work. So that's always a concern we have. But generally, we can agree that as technology improves, as we improve precision, we are getting better measurements of reality. And hopefully this can elucidate some disagreements that we might not have been able to resolve before. Sometimes it doesn't. But all of these cases of technologies that we've discussed here, if we take a step back and ask what's going on, they all kind of rely on some kind of theory, right? Like these surveys rely on a theory of, this is outside of my wheelhouse, so I'm spitballing here, but theory of, you know, honesty, of perception, et cetera. These GPS trackers rely on satellites as like a whole technology existing and working, on the theory of electricity and magnetism. I could stand here all day and tell you, well, actually people go to school for 4 to 6 years to figure out how GPS trackers work. But the point is that there are theories and there are models that allow us to understand and then interact with these phenomena. And then we build these devices with these theories and models in mind, in order to then probe the world, to probe other probes, to build cars, et cetera. But what I'm trying to illustrate to you guys here is that there's kind of this symbiosis here. To build an instrument, we need some kind of theory. And once we build that instrument, we can probe that theory deeper. We can come up with new theories or probe new worlds with it. And the circularity is a blessing because it allows engineering as a field to work, but it comes with some problems. Mainly, can we trust? And I've given you 2 cases here where your model of surveying people might not be trustworthy. One was a lot more legit than the other. And then there's 2 ways in which we, you know, need to be able to trust this theory. One is in the process of building that device. Can I convince myself that I built a tracking device? And then the second is that, does this tracking device actually work? So there's a lot of steps along the way of theorizing, testing, back and forth. It's a very nonlinear process. And so hopefully we've touched enough on this question of how do we know an instrument works. Does anybody have an answer to this? How do we know? I kind of mentioned the word earlier in passing. Calibration, exactly. So once we have an established method that we can all agree that works, we can now use that method to then answer whether this new technology works. So as an example, when you were in high school biology, you probably learned about different electron microscopes. To make sure that electron microscope works, you have to be able to show that it at least produces the same results that an objective microscope produces, right? You calibrate it against a trusted existing technology. And you can come up with we can come up with analogs in a lot of other technologies as well. And this is a process that happens after we've established this chain of scientific, or this pyramid, if you will, of scientific progress and technology that underpins that device you're using. In this case of electron microscopes versus optical microscopes, you have two totally different fields of physics that are producing the same results, right? So building out these trees of technology and progress can get kind of hairy, right? So it's not just sufficient to know that the objective, confocal microscope works. That won't tell us anything about whether the theory behind the electron microscope works. You need to establish that the theory of the electron microscope is sound, and then build it, and then test it against the other type of microscope. So there's establishing consistency within the technology of a field, and then between technologies across two different fields. And we do this through measuring known quantities. So, I would have to know what the grain of wood looks like if I wanted to measure it with these two devices before I put it under the microscope. And if I received a mystery substance from somebody and put it under the microscope, I would have no way of knowing whether what I saw is what's really there, and then I would have no idea of knowing whether this microscope works. And so you can ask the question of how do we actually calibrate reliably? And this is a process of essentially, being able to measure the inputs versus the outputs. So if I have one grain of wood and then I rotate it some angle, I should know how the light ought to reflect off of that, how that image should change. If I rotate my wood and then it suddenly looks like a piece of steel or something, and I don't have an explanation for why that might happen, right? So you need to have some consistent internal logic for this calibration process so that you can know how changing that object will change the measurement that you make. If I turn off the lights in this room and I don't see anybody anymore, I know my eyes are now detecting light, right? And so I think hopefully what I've convinced you through this slide is that this process of both creating technologies, testing them, calibrating them is a pretty difficult, relatively not straightforward process. And there can be a lot of troubleshooting involved. And like I said earlier, there's two main forms of troubleshooting that you often need to do. One is in the engineering, so understanding does this string of theories make sense? Is the principle behind my object sound? And then second, have I built it properly? Have I built it to spec? And so often, engineering is a lot of back and forth between construction and engineering itself. And this is why, projects go over budget often. Things take a long time, etc. Are there any questions so far? Okay. So this is a preview for what we're going to be doing next time. we have some fun toys to, well, they're scientific measurement devices, but we can use them to have fun. And so we're going to be testing the light spectrum and calibrating it to our eyes. You know, hopefully what we read through this device agrees with what we see. And then we will also be measuring some motion with our phones. So stay tuned for that. And I think that's all we have for today. So
We have 5 minutes.
Yeah,
It's
yeah,
okay.
yeah.
Several people had questions about some logistics, so we can take, a couple minutes to address them. One of them was the use of AI. And so, wanted to just have an opportunity for you to ask questions if you have any. Basically, for the assignments, there's 3 modes, and you can choose, one of the 3 modes. The first mode is human reasoning only. That's when you turn off AI and say, I just want to learn this myself. And then once I have this, I can, get back to involving AI. So that one's straightforward. The second one is a hybrid mode where you use it, but you add a footnote as explaining how you used it, right? And then the third mode is the one I think that caused some confusion, which is a much more explicit exploration and use of AI, right? And so that one would, for instance, for the poster topic, mean that you choose a topic, whatever topic you already chose, and then you figure out your own reasoning while you're exploring the AI's reasoning and in more complex ways, and then add basically a meta layer or an evaluation layer to the poster that explains how that exploration worked, right? So to give you an example, you could set the AI up with different personas and have it play a role of a challenger to your own ideas, and then see how that's going, right? And so, for instance, you're a physicist and you have a hypothesis within that realm, and then you take somebody from, you program it, you give it instructions to say you're a biologist or somebody who doesn't believe in science. And so then you keep testing, your own ideas vis-a-vis, that persona, and then see if it can generate ideas that actually make sense to you or not, or if you feel like this is not working, or how does it improve an understanding of your own reasoning, and vice versa. Do you learn something about how it reasons, right? So I think that third mode makes mainly sense if you already feel pretty comfortable with the scientific reasoning concepts and with AI use. If you feel like, no, I don't feel comfortable with either, then maybe the first mode or the hybrid one makes more sense, right? If you're interested in the third one, which is a bit more complex, feel free to reach out to us and discuss that, in a little bit more detail. And so any questions, about either the AI use or any of the weekly assignments, the poster assignments. I also sent out an email about using the poster reception slot for the last class. So, we won't use the finals slot on May 29th and instead hold that on the 22nd. So, any questions?
I have one more logistical announcement, which is that totally my fault. When I was describing option 1, I said discuss how you might, I don't know, I made it sound very hypothetical and everything. I apologize for that. What I really mean is if you're choosing option 1, really do describe, show your thought process as you go through and actually apply the topic to your poster topic. And in the end of option 1, you should say how it helped, which direction it pushed you in for the answers to your decision poster. Don't just say hypothetically what you would do, but actually do the combination of your poster topic and the course topic. So no, Margaret, you did that already, but going forward.
Yeah. Any open questions about logistics, assignments, Canvas, ed discussion, improvement suggestions?
For the discussion, they were supposed to post for, it was supposed to average 1 a week on each topic. Does that, are we supposed to average just typing something on Ed, like either a question or a response, or is it specific
To respond.
to response? Okay.
Yeah.
But you would also like us to put more questions.
Yes,
as well.